We are ready to start learning about the normal distribution. Well, actually, we learned about it when we learned about continuous random variables in general. But in this section, we're going to get into it in more detail. What kind of random variables would be considered normal? One example is shoe size. If you ask enough people about their shoe size, you will find that your graphed data is bell-shaped, like a bell curve, and can be described as normally distributed. So these are situations where you have a mean in the center and most of the values tend to pile up around that mean and then start to taper off in each direction, creating a bell shape. And we can model this using the probability density function, f of x. Now, f of x would represent your height or your y values, your vertical location, when you plug in certain x values. So if we take any possible value of the random variable that could lie along the horizontal axis and start plugging those in and plug every single possible one in along with whatever the mean and the standard deviation are, then you'll get xy pairs that will create dots that would make a bell curve like this. Now we don't have to do this. We're not going to have to work with this equation at all, but it's useful to know where this bell shape actually comes from and what we mean when we say a bell curve is defined by its mean and standard deviation. The mean will define where the center lies on the horizontal axis or on the number line, where the center of the bell will be. The standard deviation will determine how wide and short the bell is or how narrow and tall the bell is. If you have a large standard deviation, you will see a wider, shorter bell curve. And if you have a smaller standard deviation, things are more squished in and make it taller and more narrow. So now area is going to represent cumulative probability. So we're not actually using the bell itself to find our probabilities, but we're using the areas underneath the bell. And the horizontal axis represents your random variable. And when you want to know what's the probability in this example that my random variable will fall between 1.8 and 2.75, for instance, then I would want to know this area shown here. So how do we find an area like that? Well, when we learned about continuous random variables in general, we were introduced to the normal distribution with the empirical rule. And the empirical rule states that if we have a normal bell curve, then we can expect 68%, let me do a little highlighting here, about 68%, so it's an estimate, of the values will fall within one standard deviation of the mean, right? So if you go from the mean to one standard deviation out this way and one standard deviation down, then you'll have 68% or approximately 68% within this region here. And so if we were to find the area in between those two, it will be about 0.68 as a decimal. Okay, then we have that if we had 95%, we could expect that to fall within two standard deviations of the mean. So from here to here, all the area under the curve, in between those two values, would be have an area of 0.95 approximately. Okay, so we can expect that as an estimate. And finally, the 99.7% would fall between three standard deviations. And notice that's almost 100%. And as you can see, the bell curve gets very, very close to the horizontal axis at that place. You know, when you move that far away from the mean, the probability density function is almost touching it, but it's never ever completely touching. There's always some area still underneath going all the way towards infinity and negative infinity. but those probabilities get extremely tiny the farther you move away. So we know that we have almost all of the values falling within the range of 3 standard deviations from the mean. Now that's nice. We can do estimations that way, especially if we know exactly how many standard deviations, if there's a whole number of standard deviations that a value lies from the mean. But sometimes you might be only part way, only part of a standard deviation away from the mean. And so we need something that's going to do better for us than just giving us these guidelines as approximations. So what else could we do? Well, the other continuous random variable that we've learned about so far would be a uniform distribution, where the values of x are equally likely, so you get a probability density function that is a straight line. And so to find the area under that probability density curve, you can just create a rectangular shape and find the area using base times height. Okay, so we learned how to do that. Can we do that with the bell curve? Well, if we did, for this example, notice that the area of this rectangle would be much larger than the actual shaded region under the curve. Now we could try breaking it into smaller rectangles and we'd start to get better estimates. However, we'd have to keep doing this and trying to get smaller and smaller rectangles. And this is the concept of Riemann sums, that is the basis for integral calculus. And with integral calculus, what you do is you keep making these rectangles tinier and tinier widths so that you get better and better estimates. Now, we're not needing to do any kind of integral calculus in this course because we have the cumulative distribution function, or the CDF, which is going to go ahead and find that area for us using technology or a z-table. So the probability CDF, cumulative distribution function, gives cumulative areas under the bell curve. And when you see a shape shaded like this with X marked on the horizontal axis, this shaded region could be denoted as the probability that X is less than some specified value of X. All right. So there's 3 things we can do to find areas under the bell curve using these 3 approaches. We'll be estimating using the empirical rule, look up in the z-table, and use technology. Now in Excel, that is norm.distribution, where you would plug in the boundary, which is the x value on the horizontal axis, the mean, the standard deviation, and we will always choose true for cumulative. If you can think back to when we did binomial random variables and we used binom.dist in Excel, we would sometimes choose false for cumulative when we wanted the probability of an exact number of successes, and sometimes we would choose true if we wanted the probability of x or fewer. Well, we're never looking for the probability of exactly a certain x value because there's infinite possibilities here, not like with the discrete random variable where there were only a set number of possibilities. Here we have infinite possibilities, and so the probability of landing right here is almost 0, and it's as good as 0. So we don't find the probability of exactly x equals x. It's always x less than x or x greater than x, always a cumulative probability. In the next video, we'll start working on some examples, so I'll see you over there.